Professor? Tell me.
Yes, we can hear you.
Okay. Hanam University, South Korea. Now I'm in Korea because of the COVID. I'm here. Okay. Just a moment. My talking is this. This one. Now you see here. Just a moment. Something wrong. Just a moment. Tell me. Okay. So moved. Okay. Now here. Now this is this is deep learning. The construction inputs at the dense layer. There's some the decision layer and some loss. From here to here, x2 input to loss. We call this forward propagation. And this, we have to know this weight and the bias. For this, we have to have the back propagation, means from loss to here. By using the gradient algorithm, gradient descent algorithm, we use this one. Let me explain from now. First, let me introduce a forward propagation, means input x2 loss. We call this forward propagation. For this, let me explain artificial neural networks. Here, we have to know affine transformation and active functions. Next up, let me explain the dense layer. For constructing this, there are two kinds. Those are sequential method and the functional method ways. And also, for final layer, we need signal function, otherwise softmax layer we can use. And then loss function. There are four kinds of the representative methods there. One is mean square error. This is for regression model. The binary cross entropy error and the sparse category cross entropy. The category cross entropy errors here. Let me explain four kinds of these loss functions. And then let me explain the backward propagation for getting the weights and the bias. For this, we will use gradient-based algorithm. For applying this, we use linear regression and the logistic regression and the multinomial classification with the MNIST. Let me explain this one. Today and tomorrow, I'll give you some very brief, very roughly. I'll introduce you this one and the main theory and implementation also. Okay, next, okay. Okay. Classification of machine learning is, as you can see here, machine learning, there are main three purposes. Supervised learning and unsupervised learning, and the reinforcement learning this. Okay. Today's topic is in machine learning and the supervised learning. Here there are two kinds, regression model and the classification model. Today, let me explain about this part. The regression and the classification. For this, how to get weights and the bias. This main topic is how do we know the weights and the bias. Okay. Artificial neural network is like this. As I said already, input is here. This is a neuron, and we call this dense layer. This is a dense layer, and the final dense layer is we can use sigmoid. Otherwise, we can use softmax. From this, we can get the loss. Loss means difference of real value and expected value here. Real value is from here, we can get here. Then we can get, compare this one, and we can finally get the loss. From loss, we know the loss. By using this, we have to decide here, weights and the bias. We call this a back propagation. This is a forward propagation. Here to here, forward, this backward, this one. Okay? Today, let me explain about this concept. First of all, let me explain function means. Function is here, and the parametric functions here. Function means, as you know, x inputs. Then here, this is the function of x. Then we can get the g. For example, e power x or log x, something like that. We can do that. This is a function usual we can use. Parametric function means here, input is here. The function includes the parameters here, data. This is not input. Then output depends on the input and this parameter. Therefore, for example, G equal input x plus parameter data, otherwise data x. Many times you can do that. Anyway, we can use parametric functions, means x and parameters. Important how to get this data. Deep learning means how to decide the parameter data, and also this data is very huge numbers of data. How to get this? For this, we can use a back propagation. Okay? About this, let me explain from now. Okay, then first, let me explain what is the neuron. Now you can see here, this is input, this dense layer, output here. Then one by one, this is, we call this a neuron. Neuron is okay. Neuron consists of two functions. One is affine function, another one activation function here. Like this here, affine function and activation function. This is one neuron. So each neuron has these two functions. One is affine function and activation function. Then what is affine function? It means here, for example, x input x is here, one-dimensional, as we call xw weight plus b. W is weight, b is the bias. We call it affine transformation for this G. And also, sometimes, usually, x is many dimensions. It's n dimensions. N dimensions x1 to x over n. In this case, we can represent the vector formats. Here, like this one, x of t to w plus. In this case, also, w is the column vector here, like this one. Okay? xt transpose x equal the row vector, w weight vector equal this is column vector. Okay, this is the in case of undimensional input here. Anyway, important thing is one by neuron. Each neuron has two functions. One is affine function, another one activate function. You have to remember this one. Okay? Up to this other question, please. Okay, let me explain. Let me continue. Okay. Then, just before I explained the affine function, and what is activation function? Activation function means, now here I said here, input, this is affine function. Another one is activation. We call this neuron. Okay. The output of activation function, we call this A. A equal function G over G. Okay. G equal this one. X of, this is G. Okay. This is G. Then function G means activation function. The most important, most representative activation is this one here. Sigmoid, 10h, and the value. Okay. Sigmoid means 1 by 1 plus e to the power minus g, and the 10h means like this. You can use this one. And the value means maximum 0 to 0 or to 0. This maximum value. We call this value. This most representative activation functions here. Okay. Today we will use this one. Okay. Next. Now here you see here sigma the function is here. Now this is input, and this is output. Now you can see output equal between 0 to 1. This means probability. Therefore, the output of sigma function is, we can say, probabilities. Okay, and this is 10h. It means input, this output is between minus 1 to 1 for this one. And the value means this input, output is 0 to infinity for this. This is a value, and then the 10H, the sigmoid. This is the graph of the activation function. Okay. Then, what is output of the neurons in this mini batch? Now here, mini batch means the number of the data X is some number of some data, n numbers of data. Now here, X1 equal 1 to n means n features. To n features, it is a data here, n numbers. We call this mini batch. Mini batch means input is n numbers here, large n numbers. Then, of course, for this we have to use this weight equal column vector this one that is exist on the real numbers here. Okay. Then output activation means A1, A2, A3 to AN we can get. Okay. From this we can this is G1, G2, G3 like this one. So therefore, generally we can represent output of activation function A equal G over G equal G of X of T into W plus B. Okay. Now this is the output. Generally, representation like we can represent this one generally. This is output of artificial neurons. Then, so far I've explained the graph of sigmoid activation function. This sigmoid 10H value, we can implement it here. And also, second implementation is how to get output of neurons, means applying function activation sense. Let me implement this code by using the Python. Okay. Now, okay, let me move to the Python program here. Okay, now. Okay. First, let me explain graph of sigmoid 10H and the value. For this, we import numpy, the TensorFlow, and for using the activation functions, we use the TensorFlow keras layers. Under this, we can get activation imports, and for graphing, we use the MATLAB library. Use this one. Okay. Okay, first we have to make the inputs. Input means now this is input. Input horizontal X is here. Input equal G. G equal here minus 10 to 10 minus 10 with 100 intervals here. Okay, this is input equal G. G equal here. And activation functions, you can get activation from this. Activation sigmoid, we call this sigmoid, the 10H, and the ReLU. In this case, input equal input G. Then here we can get the sigmoid function. From this we can get the 10H function. From this we can get the ReLU function here. For plotting, we need to plot 3 plots. For this, we have this one by using axis concepts. Okay. Then first, signal function, first graph, fusion function, we change the G into numpy format, and title, X label, Y label. Okay. Second is the 10H is also second graph is the 10H is by using the 10H and the X label, Y label, and the plot G equal numpy 10H here. This is X axis. This is the horizontal axis. This is vertical axis 10H. This is sigmoid vertical axis. Value also horizontal axis is G input and output is value. This one we can change the NumPy format. Then we can get this one. Okay, let me execute this one. Okay, here. Okay, for this, for executing this, we can get here. Okay, click here, advanced control. Get space and enter. We can get also. Now I use this one. Click this one, and we can get the now is it executing. Okay, finished. Now then you can see here. This sigma the function, and this is input, and as I said, output is 0 to 1. Therefore, this we can call this probabilities. Okay, this sigma function is like this one, and the 10h is input is here logit, and 10h equal -1 to 1. Okay, -1 to the value is output is -1 to 1. We get here. Okay. For example, input equal for example this is 1, and then finally we can get this output for this one. Okay, this is 10h. Okay, and finally value function is this one. Value function means less than 0 is all 0, but the more than 0 is the same value of g. We call this. This is 10, and after the 10 we call this value functions. Okay. Okay, this I plotted here. I use this program. I plotted the sigmoid function and the 10h function and the value functions like this one. Okay. For this code, do you have any questions for this? Tell me please. I think already I distributed this whole program. I guess all of you already executed all this one time. At that time you have some question, please tell me please. Anyone you have query? Tell me please. Are you okay? Anyway, this is the input G. This is the activation functions we can get from this. From this we can get output here. From this we can get activation functions here. Okay? TensorFlow, Keras, layers from the activation sigmoid, 10h. Except this, there are so many kinds of activation functions. But here, the most representative activation I will introduce you. Okay? And this is how to graph this one. Okay? The plot substitute. This is 3, 1, figure size equal to this one to this one. Okay, then next, let me move to here. Then how to get output of neurons? Neurons have consist of two functions. One is affine function, and another one is activation functions. Here, we can use let me use two methods. One is by TensorFlow, we can get output, and otherwise we can get output by manually. Then we can compare this value is the same or different. Let me explain. Okay, let me compare. Okay, then now here affine function with the n feature. Okay, n feature means x. N feature means x have x1, x2, x of n like this one. Okay, this one. Now here I said that this n feature 3 means x. Okay, x1, x2, x3 here. This is one neuron, just this one. In neuron, there are two methods: affine function, this is activation functions. Okay, now here W1, W2, W3, and the bias is here. Bias. Okay. Therefore, three now here n feature is 3. N feature is 3, and therefore here the output. What is the output you get here? For this x equal, we can get uniform random numbers. And now the x equal n equal to this is one number. this is one number and another one numbers here. Because n equal 2, okay? First over here, okay, let me use n equal 1. Okay? Now just can use just one numbers. Okay? And with the 3 and x make some 3 into 1 vectors. You can make x input. Minimum value 0, maximum value 10. And here shape you can do see that. Okay. Now here let me execute. Let me check the x. Okay. Now here now x equal this. X equal, now you see it is 1. Just I generated one x n equal 1. For example, n equal I have to 5 means 5x, 5 inputs. Then here you can use this 5 1 is 1, 2, 3, 4, 5 minutes. Okay. For simplicity, now this time, let me have some n equal 1, just one numbers into that. Okay. Here, now from this, there are three kinds of active functions. From this, we can get the inputs command. We can select one of these: sigmoid, 10H, and the value. Okay. And the dense layer equal this one. Dense. Now here, unit 1 means just 1 is now here, 1 activation here, and activation means activation here. We selected the one, this one activation. From this, we can calculate output by tensor flow. Is just we can use the tensor x is enough. X equal input, the dense layer here. Okay, dense is already this. Now here I defined here. Unit equal 1 unit activation pin activate here. Because the dense layer here, the object is we are using the dense API objective here. Then we can get it and the output of this output of activation person by tensor flow. And simultaneously we can test the weights and the bias by get weights. From this we can get here. Okay, now, okay, check this one. Okay, now from this, okay, now here, so let me check the weight and the bias here. Now this is select the sigmoid. Okay, and in case of sigmoid, x is 1 x is here, then the weight equal this one. Okay, therefore the shape is 1 by 3. Therefore for matrix multiplication we need 3 by 1 is here, and the bias 1 is. Okay, this is one. Okay, then next okay, let me do this.
You will now be placed into the conference. Please press star to continue.
Then output of neuron by manual means now here G equal linear algebra the matrix multiplication x and w plus b. Okay, and in case of equation sigmoid we use this one. Okay, this is sigmoid function. In case of 10h is this one. Exponential power g minus exponential minus g by this one. This is 10h expression. And the value is this one. Maximum or 0 or 0. Get this one. Okay, then okay, let me here check. Now here, for example, now here 10h. Then you can get here x equal 1. This is a 1 by 3 matrix array vector. The from this you can get a weight. I use the dense, and here output of neuron, output of activation function A is by tensor flow. It's this value, and by manually this one. Therefore, now you can see here two same values you can get by using tensor flow. Otherwise, by using manually you can do that. Therefore, many you can use the tensor flow is okay. Yeah. Now I compared you can see a same one. Okay. And let me have some more example here. And equal, for example, three inputs. 3 input. And let me check this one also one more time here. This time because it's a value. Okay. Value. And here. Then I assigned 3 numbers of input here, here, here. Also input is 3 dimensions, 1, 2, 3. And the weight is this one here. The bias 0. Now here output, our neuron is 3100. This one, this one. Okay. Now this means I said value means now here because let me explain here. This is value means 0. This one. Therefore, all this input is all less than 0. The output is 0. Now this is now you can see here. This is what I want. The output is minus. Then we can get this one. Another one. Let me check one more time, please. One more time. And now here this time also here you can get here. Now this x equal 3, x is here, weight is here, bias, and output is like this one. Now here in this time this one. For first x you can get this one. Now this means here x equal here, output equal here. Okay? And another x, for this x is output is this one. Another x is, you can see output our equations here. Also here you can see by tens pro, I mean this one is same. You can compare this. Okay. Okay, then next and let me explain dense layer. Okay. First session I explained about this concept. How to get that, how to know this X input, and this is one neuron. I explained up to this. This explained. Now this time, let me explain this part. This part we call the dense layer. Dense layer. Let me explain. Okay? Dense layer. Okay, dense layer means here. Okay, now. Now your dense layer. This is all your this neuron. This is neuron. This is a neuron. This is the first layer. We call this the first dense layer. Dense layer. This is second dense layer. Third dense layer. This is output. Okay. Then input here. There's also now here output of first layer. We call this A1. This is A1. Output of this is A2. Okay. Therefore, first layer input equal X. Second layer input. Second layer input equal this is input. And the third layer input of the third layer A2 is input. Then finally you can get output here. Okay. This is the dense layer. Okay, for constructing layer, there are two methods. One is a sequential layer, and another one is a functional layer. Okay? Now first, sequential layer means it's very easy to use and very common. But in case of very complex network with multiple input and output, sequential layer is not proper. Okay? For this one, input, and goes to first layer, second layer, final output you get this one. Okay, this is the layers. Okay. Then functional layer means now now here hidden layer, first, second, third one, this one. In case of sequence layer, the input is must be here, okay? But in case of this, we can make this one in time here. Also, we can make this go to here. For this, we have to make this one. Hidden layer 1, this input equal this, and in hidden layer 1, this one. This one is, in this case, we have to mention input like this. Input is input. What input here? This is hidden layer 2 input equal hidden layer 2 this is input. In this case, this layer input is what? Now here, hidden layer 3. Hidden 3, this is input and also input. This is also input. Then we have to make input here. Therefore, you can make to this one. And you can do this one from here. Therefore, in case of sequence meter certain, you can use this here, here, here. 1, 2, 3, 4, 5. But function means we can control. First 1, 2, here you can do that. Or here, 2, here you can do that. Now just you have to mention this input here. That's all.
You will now be placed into the conference. Please press star to continue.
Okay. This is functional layers. See here, okay, understand it here. Now I explain the inputs. Okay. Then for representing this kind one, now I said here, and the first layer, the output of activation is we can this one, and the activation function we can get output here. The second layer input is this is an input, therefore input and the W2 plus B2. Okay, and through the G activation function we can output here. Then finally you can get a previous activation function output of function and the weights and the bias for this one. Okay, therefore this input. For this input is input. Input means output of activation layer, first layer, and output of this this goes to here. This is output of the activation of this layer. And finally, we got this one. Okay, and finally, last dash layer, we can make a sigmoid. Sigmoid or softmax. Now first, let me explain sigmoid. Sigmoid from this odds function. Odds function means p by 1 by p. Now you can see the probability. We call this odds, okay? You know. This value is with the 0 to infinity like this. 0 to infinity we can get here, okay? This odd function. Logit means by taking this log to odd function, we can get the logit. Then the output is minus infinity to infinity, this one. This is the minus infinity to infinity, this one. Okay? Input. This is the probability. Okay? We call this a logit. Okay? Logit, one more time. Logit means odds. We can apply, we can take logarithm function to with this odds function. Because this is logit. Then what is sigmoid? Means sigmoid means, as I said, this is a logit. This is a logit. As you can hear. From this, we can get P. Then from this, we can get 1 by 1 plus E minus L. This is logit. Because this is sigmoid functions. Now you can see this is certain one probabilities. Now you can put here. Input is here, input, and this value you can get here. You can get here. Just only one probability. One more time here. X, applying function is equal xt plus b, and this sigmoid function we can get only one probability by using sigmoid. Okay. Now please remember sigmoid function. You can the input. that goes to the sigmoid function, finally we can get just one probabilities, not many probabilities, one probabilities. Now from this we can get one probability. We call this sigmoid functions. Okay, this one functions. And then sort function means just one word. K inputs, K number categories changed to K probabilities. K probabilities. How to make probability? You can use this one, this value. Okay, this value. Now here, output of this A1 to K. This is K category belong numbers of categories. Then from this we can get the probability here P1 to PK. Then therefore summation of this equal what? 1. Okay, this is the probability Y. We call this this value equal Y hat means expected value. Expected output. Y hat is output. Expected output. Real output is from this. We can get out real output. This is the real output. Okay, expected Y hat. Like this, X density layer. Finally, we can get this it's called the softmax. Then finally, we can get the probability. K numbers of probability. In case of sigma, if you use sigmoid function, we can get just one probability. But if we use softmax, we can get the K numbers of categories. Understand? Please remember, in case of sigmoid, okay? In case of sigmoid, just one probability. Okay? Now here, as the sigmoid function, we can get one probability. But in case of if we use softmax, okay. Just so sorry. Now is it some? Here's some. I'm sorry. Let me check. Okay. Softmax. Okay. Okay, softmax. Okay, softmax means K numbers of categories changed to K numbers of probabilities. You got the softmax. So far, I have explained input and dense layer and the sigmoid softmax. This part I completed. Okay. For this, let me have some implementation, and let me continue for the lots. Okay. For this, okay, dense layer construction. Okay, let me put this one here. First, we use sequential method. For this, we have to import TensorFlow and from the dense layer sequential. Well, now, what we have to do is first now here implement 3 dense layer instruction. Construct layers for binary classification, and then one other is construction for the multinomial classification. Multinomial multi-class. Binary means k equal 2. This is k equal more than 2. Okay, the binomial. In this case, number of data and the 4 layers. First layer is 4 neurons, activation is sigmoid. Second layer, 10 neurons, activation is ReLU. Third layer, 7 neurons and activation is 10. Final layer, in this case, in binary case, we have to use sigmoid. Okay? And finally, you can get the input and the expected output YL. This is real value. This is Y hat means expected value. Okay? And also here, same layer, just another final layer. This is not get this K. Okay. Final layer, we have to make K neurons for multiplication. Understand? Now here, first, second, third, fourth layer here, final layer here. Please pay attention to this final attention. In case binary means just one neuron. And we have to use sigmoid. Now for multiplex, this final is the K neurons. Activation, this is softmax. Now we can get here, okay? Okay, let me implement this one. Okay. Now go to here. Okay, now for simplicity, first let me use n equal 1. Just the one numbers. P is equal 2. Therefore, x equal. Now we have to use here. Okay, now here x equal x1, x2 is here. And the first layer is 4 layers. 4 neurons. 1, 2, 3, 4. Second layer is neurons go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Third layer is 7. 1, 2, 3, 4, 5, 7. Then we can here, all we can connect. All connected. Then finally is sigmoid percentage here. All we can. Okay. Therefore here xk equal 3. Okay. In binary key, it means this. We have to make a dense layer. First of all, with the sequential, by the sequence layer, we have to, by using the API with the object, model object, you can make sequence here. From here, we can add. You can model add first 4 neurons. This is the 4 neurons, okay? 4 neurons and the sigmoid. Second layer, 10 neurons. This is the 10 neurons, okay? 10 neurons and the equation value here. The third layer is 7 neurons and 10 H. Now, finally here, it depends on input in case of binary and multiple case. In case of multiple, you have to add more on this one. This is therefore 1, 2, 3, 4 layers. Okay, 1, 2, 3, 4 layers. The final algorithm is the neuron sigmoid. In this case, it is a binary case. But mode is multi-case means now here you can add the final this is called k equal 3. 1, 2, 3. Because k equal 3. Because now we are using the category number k equal 3. Okay? Now k equal 3. In case of M, you can add the k neurons and the activation is softmax. Okay. The more important thing, the final layer here. In case of binary, is one neuron and a sigmoid. In case of multi-class, this is k number of neurons and a softmax. Then we can add this one. Okay. Okay. From this, okay, let me do this one. Then here, enter the mode binary. First of all, binary please. Okay, binary. Can add. Then you can here x equal just one n equal 1 number 1. Now this is number data is n equal 1. That the feature equal 2. Therefore x equal just one number factor x1, x2 here. In this case, output of sigmoid is just this one. Binary case. Okay? Binary case. Then next, one more time here. In case of a multi-case. Multi-case now k equal 3. Then from this, input, x input here, then y hat equal, output equal 3, category 3, therefore output of 3 categories here. This one. Equal to 1. And from this, the most important, the most highest one is this one. This is category 0, 1, 2, 3. This x is equal to 0. So we can do that. You understand? From this, we can get this here. Now, all this is probability equal 3.7, and this is 23, this is 39. Okay, that is most highest one. Therefore, we can do this one. Yeah, maybe this is dog. This is category 1 equal cat. Category 2 equal cat, bigger dog. Category 3, 1, 2, another one is monkey. And in this case, 2 is this. Therefore, input can be assigned monkey. We can categorize this is the monkey because this is highest one. It's highest one. Okay. This one. And also, y hat means we have to sum of this one. Output is equal 0, equal 1. Here you can come from this. Okay? Understand? Okay, let me have more. Explain to this. Okay, let me have okay, now here. N equal, for example, 3. Okay? 3 and, okay, not 3. Okay, you can get it. There's a 3 x's. And now here's a multi-case. Multi. And now here, let me check. Now here, okay. Now here, x equal this is one input, another input, this kind of input is here. Then your first input is this one. Therefore, first one and this is maybe this highest one. This is a monkey. Second x is here, and the highest one is this one also. This is also monkey. The third one, this is x. This is also highest one. This is also monkey. We can this one. Okay. Let me shoot one more time. Okay, now here with the server multi case. Now here. 3 inputs is here. 3 inputs. Okay. Okay. Now this is for this input. The category is this one. This is dog. This is x1. This is a dog. You can classify. And the next, this is input. We don't know what the actual this is. Okay. Now this is the highest one. This is a monkey. Although this x for this highest one is also this one. This is also monkey. There are so many monkeys. Anyway. Also, from this, all this addition of this equal 1, addition of this, summation of this, all this or this one. Okay. Now this means I explained here. Now this, all this variable here, we have to add this in 1. I explained. Okay. Okay, now here. Okay. Now I have explained this part. Input, complete, and the sigmoid and subter. Sigmoid means just one neuron with the sigmoid activate function. Subtermax is the k numbers of neuron output by using the subtermax. Okay. Up to this any question, please. Tell me please, someone please.
It is, sir.
Asrin PT, are you okay?
It is, sir.
Yes, we can hear you, sir. We can hear you.
Okay.
Okay.
Please continue.
Okay, let me continue, okay?
Yeah.
Yeah, next, how to, the loss, okay? Loss means that the between expected value y hat and the true value y. Okay? Now here, okay, from this loss, yeah. Here, loss function, for regression, we use mean squared errors. Okay, for regression, we use mean squared errors. For classification, we use three kinds. This is binary cross entropy errors, the sparse categorical cross entropies, and the categorical cross entropy errors we can use. Okay. For regression, we use a mean square error. Okay. For classification, this is okay. For binary means k equal 2, we use binary cross entropy. This is k equal more than 2. You can use a sparse categorical, otherwise categorical. Now here, B means categorical, this is 0 or 1. C equal k categories. P equal probabilities. R equal real continuous value. Okay? This is it. Okay? Please remember this one. Okay? For regression, we use a mean square errors. Classification, this one, binary, sparse, categoricals. Okay? What else? Let me explain now. Okay. First, what is mean square errors? Now, X and the label. For example, in this label equal 23. For this label equal 25. For this label equal 36. Label means answer, target. Okay. Now we know input and the labels. Then we are using supervised learning. We call this supervised learning. Therefore, this one. Okay. Therefore, x equal n dimensions here, and also y equal n dimensions equal. So 1 by this. For this, label is 1 here, 1 here. For this, we can use mean square errors. How to use this one? How is that? Okay. Okay. Now, mean square error is very simple. As you know, this input. Okay, and dense layer. Finally, we can go to we can output the equation and expected value. Value for this y hat. We can give y hat. Okay, and from this we can get y is here, real value. The real value minus effect value whole square, and then average. Okay, and numbers of data. Here, in this case, there are no activation functions. No need. Okay, there are no activation functions. Last layer here, this is a final function, and the activation function, and the final layer, there are no activation functions. Okay, this is mean square errors. Okay, for this. Let's implement loss function. Number of data, batch size, and generate input x, y puts the normal random distribution, and from this construct the data set. And also for this, first layer, 7 layer input, 4, 5, 6, 7, and input equal here, go to here. For the second layer, this is the value. And the second layer is 5 neurons, activation period is 10H. Third layer is just one neurons. There's no activation functions. Okay, this was it. And we can add it here. We can get finally you can get this y hat. And then from this you can get y. We can square and summation y1. Then you can average. Okay. Well, let me do this. Loss function mean square error here. Okay, for this, tensor profile is the important tensor, the mean square error, and the sequential. Okay, and first of all, just a number n equal 1. Okay, now batch size, let me explain here. When we have many data here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers here. For this, we have to use just the batch of 3 measure. 1, 2, 3, like this one. This is 3, 3, 3, we lumped, and then we can get this one. Get this one. Not one by one, this one. Let me explain next time, tomorrow, maybe tomorrow. Let me explain once again. And for generating the x data and the y data is x equal random number normal here. The number equal, now in this case, n equal 1, 1, 1, make 1. And y is normal distribution here. It's the labels. Okay? Okay, let me check here. Dot comment. Okay, execute. Then here. Now, x equal input just 1 here. Output layer is equal this output this one. Okay, this label data label. Okay, let me more data. Okay, now and equal 5 data and the 2 features. Okay, 2 features, and you can get here x equal 1, 2, 3, 4, 5 data, and then with the 2 features, 2 ranges, and y, this real value. For this real value equal 1, for this real value like this one, you get here. Okay, okay, let me comment this. Okay, okay, for using that minimum, for example, now here, n equal, for example, huge number of data here. In this case, we have to make some of the package. This we call this batch size. Now here, just we use 10. Possibly with 10, and the batch size 3. There were 3, 3, 3, 1. Can use. In this case, we can use 3, 3, 3 to 1. First batch of 3 numbers of data, 3 numbers of data, just don't match here. Okay. And they generate X data and the lab data. And then for your data size, you have to make this one. Data set, you have to make from this test flow X and Y by using batch size. Now, X and Y, we can slice with the batch size. Therefore, this means 10 numbers here, we have to slice by this. Okay? Then you can data set is making it. The model is here, 3 layers. Now we have to, by using this API object model, here we can add first layer is 7 neurons and activation is value. Second layer is 5 neurons and activation is 10H. And then finally, is just unit 1 and then no activation functions. MS is, I said, no activation functions here. Then also, mean square error. We use it here from this mean square error. Okay. from value mean square error, we have to make one lost object. Okay, then we can calculate the y hat. Okay, y hat. Now here. Okay, now let me. Okay, now here. Okay, for simplicity, we equal just one. Okay, just one. For simplicity, to this. Now here, data set, from this we can get the x and y. This is real value. And x goes to model here. Model means here, we added this one, is the dense layer. We apply this input to dense layer here. Then we can get the finally y hat. Expected value y1. Then from this we can get the real value and this y hat value we can get. By using this object mean square here, we can calculate the loss. Okay, and also this one. Okay, let me check. Now here, just one data is here. Okay, now real value equal y equal this value, but y hat equal this value. Okay, real value. So 1.066, but the expected value equals 0.0. Now here there's no weight training. Without any training, we use this one. Training means maybe tomorrow. Let me explain. Yeah, without any just we are doing fold propagations. Okay, we can get here. The loss equal mean square equal like this one. For example, around this 0.5, 0.1 square equal 0.2, anyway, almost the same. Okay. Now this is it. Now this value 1.066 minus 0.53 square equal around this one 0.25. Anyway, we must save this one. Okay, and also we can use here now n equal 110 10 numbers here. Then let me explain one more time here. And now here, first batch 3 is real value equal this value, expected value equal this one. Second one is this real value, expected value. The real value, expected value. Then every for this three numbers of data, every loss is this one. The second batch. Now this means now let me do this one. Now first the data x1, x2, x3, x4, x5, x6, x7, x8, x9, x10. 10 numbers. Now for this batch 1, 2, 3, 4 is here. For this, the value equal this one. For this value, for the output, real value equal 1.066 something. But y hat is this is 0.57 like this one. Okay. This value we can compare this one. This is the real value, y hat value. Second one is for this is real value and expected value. Real value, expected value. For this average of this is this one. Another here for this the 1 here you get. Okay. Batch 3. 1, 2. Okay. Now final. So this is batch 0. This is batch 0, 1, 2, 3 is just one input. Now here one input I equal this one. Okay. This is real value. This is effective value. From this average equal this value. Means this is mean square. This is mean square. Okay. You understand this one? One more time, let me explain. Okay, now here I generated X input and the label here. And by doing this, we have to make a data set for the data set here. Data set X and Y slice with a batch size. For example, now 10 numbers of data here, 3 numbers here. Okay. Usually there are so many data here. Okay. Then in the case of batch size, for example, 64, 1, 2, 8, like you can use this one. Okay. And now for simplicity, just we are using 3 and just 10. Like this, you can make the data set here, and we have to consider the dense layer. Dense layer here. We have to make the this object model the by using sequential API, and then here add the first layer adder, second layer adder, third layer adder. In this case, numbers of neurons and the activations right here. The final, this is duration. Means there's no, in case of in square, there's no active functions, not this one. And also we make the object loss of mean square error. Okay, now here I can get by using this one, X and Y, this is real data here in data set. Here, Y hat means output of this. You understand it? Let me explain one time here. Model is, first layer is 1, 2, 3, 4. Another one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 7. One here. This is the model. All this one, all connected here. This model. This is the model. And this model X goes to here, this X. Then we can get output this one, from the output. This we call this Y hat. Okay, this is we call this model. Now this model. That means here this one. Okay, model added, many things added here. Then we can get this one. Then finally we can get Y hat. We can compare real one and the expected one. That's all. Then the loss object. This is mean square. This is mean square. Okay. Now here X what are the Y real value, expected value, real value, expected value. Okay. More simplicity and equal 1 at the time. Okay. So let me check the X also. This is X, okay? Let me see the X and the label. Let me see. Then one data is X data equal, this is X. The Y label, the real value equal this. Now this is this one. But the Y hat, the output of model dense layer, we can get this one. Therefore, the mean square equal this minus this of square. Then you get this one. Okay. So far I have explained mean square. Okay. Now mean square. Mean square. Okay. Next, mean square is not classification. It is just for regression model. For classification here, we have 3 errors, loss functions. Binary cross entropy error, the sparse categorical, binary sparse categorical, categorical cross entropy. category is k equals 2, just we can use a binary cross entropy error. The k equals more than 3, and then not here. Sometimes we can use a sparse, otherwise categorical. This means label is represented by the integer. Integer, we can use a sparse categorical cross entropy. Label is represented by the one hot encoding. We can use a categorical cross entropy. Okay? Understand that? Let me explain later, just more brief ways. K equals 2 categories, we can use binary cross entropy. Okay? K equals 3, okay. Then we can use label is how to represent label. K equals 1, 2, 3, 4, 5, this integer. We can use sparse categorical. Other label is represented by the one hot encoding, we can use categorical. Then what is integer, what is one hot? Let me explain now. Okay, now, in case of binary cross entropy here, input x1 to n numbers here. This is x1. Then the xyn is equal y1. y1 is 0 or 1. 0 or 1. Just two categories. 0 or 1 is enough. This also y2. This real value equal 0 or 1. This label is 0 or 1. This label. In this case, we can use a binary cross entropy. Okay. And then okay, in that case, binary cross entropy error is like this one. Because this is an average. This is a real value into log expected value plus 1 minus real value into logarithm 1 minus expected value. Okay, for example here, this is the real value, this is expected value. Now you can see here, real value expected value 0, 0 is the same. Therefore also we can expect the loss equal 0 should be 0. And then we can check this one, this is okay, this is okay. Also, real value is 0, expected 1. This is different, very different. Expected value should be infinite. And by using this, we can get infinite. Oh, this is okay. Also, in this case, real value 1, expected 1 is different. Therefore, expected also should be infinite. By using this, we can infinite. This is also okay. This is a real value 1. Expected one is 1. Then that is the same. Therefore, expected losses to be 0. By using these equations, therefore, this is correct. Therefore, in case of binary cross entropy, we can use this cross entropy. We can use. This is a binary cross entropy. Okay. Okay. Then next. Okay. Okay. For this binary cross entropy, let me have some implementation. Okay, now here, okay, true weight, number of 3, true to 1, 2, 3. This means x and y is this one, y equal, this is w1x plus w2x plus b. Now w weight equal, this is, okay, now this is w equal 1x plus 2x plus b equal 3 here. Okay, right. Now this way. This is a real value. This is real value y. Okay, and first this also this value real value should be changed to 0 to 1, 0 to 1. And the layer is first layer, the 3 layers here. First is the 7 layers activation value. Second layer is 5 neurons activation is 10H. The third layer is one neuron with the sigmoid activation functions. Loss equals to be used binary cross entropy. Then print X, Y, binary output and the loss. Okay? Let me do this. Okay. Now loss function, binary cross entropy energy here. For this we can use
Sir.
Yes.
Sir. Yes, sir. Shall we continue tomorrow, sir? Because students have some other work is also there, interrupting.
Oh.
Yeah,
Okay,
8:30.
okay.
Yes,
Okay,
yes.
from this
And we will
let me
continue.
tomorrow. Okay?
Yes, sir. Yes, yes.
Okay, thank you very much, all of you.
Once again, for all the people, we will request you to switch on your screen so that we would like to take a photograph so that this is a memorable and we would like to file it for NBA also. So all members, please, sir, please, you can stop sharing so that everybody's screen will be available so that we can take a group photo. Sir?
Yes, sir. Just, I think
yeah, Kim, sir,
all this
you
will
can-
be disputed. Otherwise,
yeah.
my handout, I will dispute to you. I send to you. You mean this one?
No. Screen sharing.
No. No, I mean, I can send you this one. This
Yeah.
material.
Yes.
Then I can no need to screenshot.
No, not for that purpose, sir. We are taking a group photo for today's session. Group photo. Yeah.
Group of.
Yeah,
Okay.
that's right. So if you can stop sharing, everyone's photos will be there. We can take a screenshot. Yeah.
Okay. Please. Please.
The screen sharing, can you stop, sir? Screen sharing. That material. Yeah. Stop sharing.
Okay.
Yeah, good. So please, all members, please switch on your camera so that everyone can see and we can take a photo. That's it, please.
Oh, good. Beautiful. Can you see?
Yeah, we can see everyone.
Four participants?
Yeah, they're all there, no problem. Okay, so whoever came, so we'll just take the screenshot. Once again, thank you for all once again. Okay, thank you all. So we will continue tomorrow at the same time.
Okay.
Thank you. So finally, would like to thank all the members for coming and participating at this moment. Even though it is an evening time, thanks for coming. So it is very interactive session. On behalf of the department, on behalf of all the students and behalf of all the faculty here, I extend my sincere thanks to Professor Kim for coming in late night, even though this is a sleeping time for him, and definitely share a lot of interesting things. Of course, CoLab is very important in all the research activities. Sir has introduced this to all the members. I hope this will be picking up with all the members and we'll start working on it. Anyway, thank you so much, sir. We will continue our session.
Okay, thank you very much.
Same spirit, we will continue tomorrow.
Now it's midnight here.
Yes, sir. Please take a good sleep, sir. Thank you so much for coming. Thank you so much.
Tomorrow, please. Let me continue tomorrow. Same time.
Yes, sir.
Same time.
8 or 7 o'clock, sir. Yes, sir.
Indian time.
Yes, sir. Indian Standard Time. Yes, sir.
Okay, thank you very much.
Sure, sir. Thank you so much, sir. Yes, sir. Thank you so much.
Thank you.
Yeah, sure, sir. Thank you, sir. Bye-bye, sir. Thank you for our members to come. Okay, I'll just wind up. Thank you so much. Bye.